So now I'm changing my screen. Uh, okay. So now this is the data set as it has been mentioned that here we have this preference that is a dependent variable, and these are the 9 diaper attributes that are there. All are on the scale 1 to 7. And it is the data set where we have responses from 300 mothers. Purposely, for the purpose of demonstration, it is not having the missing observation. So all these things that are related to exploratory data analysis, where we consider the quality of the data, that we will be covering when we discuss the concept through the Python or through the scikit-learn. Anyway, so we will be running this situation. So it is there on the on the PPT also, where I have used some screenshot. So we will be going to analyze, as if we have used the spaces, we know that all tools are available and under analyze. So we will be going to analyze, then we will be going to regression. And then since the linear regression is being considered, so we will be setting the linear. So we will be going to analyze to regression, and then we go to linear, right? Now, this is the dialog box of this regression analysis, linear regression model. So we will be having this brand preference, which is our dependent variable. And since we are running it for the first time, so we will be entering all the 9 independent variable, all the 9 features in one go. And this method, when all the features are being entered in one go, this method is known as enter method. Remember, this is not the only method. There are other methods also, like forward, where each feature is being entered one by one. So at the first go, we will be having the most important one. In the second, we will be having the second most important one, and so on, till we are getting the significant predictors. In the backward method, that is also known as backward elimination, so these features are eliminated one by one. Stepwise means we are entering certain variables in one go, certain other variables in another go, and so on. Remove is opposite to stepwise. But since we are discussing it for the first time, so we are using the default method, that is the enter. Enter method means all features are being used in one go. Other entries we may discuss later on. Then we go to this button that is known as statistic. So this is the statistics dialog box. Here already estimate and the model fit are being selected. We will be using R square change whenever we use it for the stepwise method or forward or backward method. Since we are running it only once, all the features are being considered in one. So we will be getting the one final model. So there is no case of R square change. But if we use other methods, then R square change will be there. Then we have the descriptive, which gives us the basic information about these features. Part and partial correlation may be used for um, checking a particular assumption, that is known as multicollinearity. We will be discussing later on. Collinearity diagnostic is also being used to examine a particular assumption, that is known as multicollinearity. Durbin-Watson is being used to check another assumption, that is known as autocorrelation. We will be discussing that later on. Case-wise diagnostic is being used to find out which particular sample values are dominant in nature, right? So anyway, we are not considering this because we are discussing it for the first time. Then we go to the plots. Here again, plots are being used to check certain assumptions like the normality assumption and the homoscedasticity assumption that we will be discussing later on. So for the time being, I am creating these plots that will be discussed when we discuss the assumption. So here we will be using the Z residual. Here there are two important things. Z is the standardized one. I will be explaining. Residual is the difference between the observed value and the estimated value. This I will also be discussing. And in the X, we have this Z predicted, right? And we will be selecting histogram and normality plot just to check the normality of, that is an assumption we will be discussing later on. So for the time being, I am just demonstrating how these things are to be entered in the analysis, right? Then for the save, just for the demonstration purpose, I am taking the predicted value as well as the residual value, both unstandardized. Though that is, they are not required in the first go, but just for the demonstration purpose, I am taking these two. So everything is being done. Now we press OK. Now this is the model. This is the output that we get. We will be discussing different tables, not in a linear fashion, because some tables need to be discussed previously and some tables needs to be discussed later on. So this table is just, this is the variable, the top, the table, this is the variable entered or removed. It is being used just to know what are the independent variable, what is the dependent variable, and which method is being used. So whatever I have discussed, I have demonstrated the method name as well as the features, they are being mentioned here. So it has only this importance. The other tables, descriptive statistics just gives us the basic description, means descriptive tools or the summary tools like mean, standard deviation of these 9 features are there. This n are the valid observation. If we have the missing observation, then obviously that will be less than 300. Anyway, since this case is being made for the demonstration purpose, so it is not having the missing observation. So the volume of the missing observation or the problem of the missing observation is not there. The correlation table we will be discussing later on. Right? Now we will be starting with this table discussion that is known as ANOVA. So I am changing my screen. So to discuss the first concept, then I will be coming back to this analysis again. Now, we are again having this whiteboard. So now we will be discussing the first step, not the 0th step in the first go. And first step is examining significance of proposed regression model. Right. As we hear the word significance, here what do we mean by? Since we are performing the analysis on a sample data, and whatever the things we are getting will be applied to the general overall things or the population thing, right? So for that purpose, we have to perform the significance and or the significant testing. And for this purpose, the first step is to propose the hypothesis. So what is the null hypothesis? It is that the proposed regression model is insignificant. So now we will be discussing. So before discussing this purpose, let me take back to the data set just to show you, means that will be part of our discussion. Now, if we follow this data set and consider the y variable. So this is the y variable, that is the preference. Now, if you observe the y variable, that here I have highlighted this feature. So this y variable, the first value is 5, next value is 7, next value is 6, next value is 3, next value is 4, and so on. So what we observe, that these numbers are different. So these numbers are different. So we may say that there is variation in the y variable. So there we are having variation in the y variable. So preferences values are different, means there is a variation. Let us call this variation as the total variation. Now we will be discussing the total variation that is there in Y or the preference. So I have just shown you here that there are variation. Let us call this variation as total variation. So there is total variation in Y. Now we will be discussing why this total variation is there. Now since it has been presumed in the model, right, it has been hypothesized in the model that these 9 diaper attributes may have some impact on the Y. Means if the customer or the mother is liking a particular attribute that is important to her, so if that is there, so the Y will be high, otherwise the Y will be low. So since this has been hypothesized in the model, so this type of variation is known as explained variation. So explained means this variation is being explained by the regression model. This variation is also known as the variation because of the regression model, right? It is because of the regression model. Now it may happen that a particular mother may like all the diaper attributes, but that mother doesn't like the diaper as a whole. So what is the reason for this dichotomy? It is because of, means suppose a particular mother takes the diaper as per the peer recommendation, right? Or as per the availability. Since the peer recommendation and availability has not been considered, so there are some external factors also that may have some impact on the Y. So this variation may be because of some other term also, and this is known as unexplained variation. What do we mean by unexplained variation? Means this variation is cannot be explained by the model. It is because of the extraneous term, it is because of the epsilon term. So this type of variation is known as error or the residual variation, right? So this is the sum. Now in some particular situation, suppose explained variation is high. So obviously the total variation remains the constant. Suppose explained variation is high. So unexplained variation will be low. So if this is the situation, we can say that our model is good or model is significant, right? So now the question arises, what do we mean by high explained variation or low explained variation? So for this purpose, we consider a ratio. So this ratio is being termed as explained variation. Sorry, this ratio is being mentioned as F. So this is the ratio of explained variation or variation because of regression, and in the denominator we have unexplained variation, and explained variation means it is because of some other term, that is the residual. Suppose explained variation is very high. Since explained variation is very high, so the value of f will be very large. So this value of f will be much larger than 1. Right. Now since this f has been estimated from the sample data, so this is a statistic that is known as F statistic, because it is being estimated from the sample data. And this statistic has a distribution that is known as sampling distribution of F statistic. It is just a technical part. You can ignore this part also. And this sampling distribution of F statistic is better known as F distribution. Right? So this is the graph or the shape of the F distribution. Here on the y-axis, we have probability of F, and on the x-axis, we have this value of F. And here the highest value is at this point, Here we have the mode and mode lies at 1. Suppose this f is very high as compared to 1. Now since f is very high as compared to 1, so this f will lie somewhat here, just for an example. And if we consider the right tail area or right tail probability, so this is known as p-value. So if f is very high, it will be going toward the extreme right, and correspondingly this right tail probability or the right tail area will be low. So if f is very high, it suggests that this p-value is low, right? And low p-value means we reject H naught. So by default, what we take that if the p-value is less than 0.05, so we say that we reject null hypothesis H naught at 5% level of significance. So now what do we mean by rejection of H naught? Rejection of H naught means this model is being rejected. So we can say that the proposed regression model is significant. Now, as we have discussed, here the whole discussion is based upon splitting the variation. So this concept is known as analysis of variation, and it is known as ANOVA. This is known as ANOVA. So the table that we are going to discuss is the ANOVA. It doesn't matter whatever the software you will be using, there will always be ANOVA, right? So now I'm taking you to this other screen. So this is the ANOVA table. As you observe, this is the ANOVA table. So this is the ANOVA table. Now there are two types of variation. One is because of the regression, that is the explained variation. Other is because of the residual, that is the unexplained variation. Contribution of the explained is 93.49 and unexplained is 1.01. As you see here, the explained variation is very high as compared to the unexplained variation. And how we are getting? If we divide 93.491 by 1.071. So we will be getting this 87.33, right? And obviously this is much greater than 1. So much greater than 1 means this p-value, this is the p-value. So this p-value is less than 0.001. So obviously it is less than 0.05. It means we reject H naught at 5% level. So rejection means we can say that the proposed regression model is significant. Means these 9 diaper attribute as a whole is significantly associated with overall preferences, right? So this is the first analysis. So hopefully this analysis is clear to all. Right? Now we will be moving to the second part. So now I am clearing my annotation because we have to move to the another part. So now we are coming to the second part, means the second analysis. So we have discussed this part. Now, after that, the second step will be, as we discussed here. So now the second step is we will be discussing, since the model comes out to be significant, so we'll be discussing strength of the regression model. So here I'm introducing a term that is known as R square, right? So it can be written as R square or R dash SQRE. So it is the ratio of explained variation or you can say sum of square because of the regression divided by total variation. Now, here, since we are having the variation or the sum of square, so sum of square, so this total variation is actually the TSS. TSS is the total sum of square. Now, since we are considering the sum of square cannot be negative. So both terms, whether the numerator or the denominator, cannot be less than 0. So r square is greater than or equals to 0. And this explained variation is a part of total variation. So this explained variation can never be more than the total variation. So this r square will always be lying in between uh, 0 and 1. Right? Now we are going to discuss the value. So as per the output I will be showing you, our r square comes out to be 0.73. 0.73 means it would be 73 upon 100. Right? So if we connect with the earlier formula, so if we connect with this formula, it means if the total variation is 100, so the explained variation is 73. So what we can say that our proposed model means the model consists of the 9 diaper attributes, is able to explain 73% of the variation in Y or overall preference. So Y is the dependent variable. So here we can say that most of the variation is being explained by the model. So we can say that our model is substantially good. So what concept we develop? The concept if the R square is near to 1, so we say that our model is strong. Obviously, it is highly subjective in nature. So I am not saying that above this value should be regarded as strong and below this value should not be regarded as strong. Anyway, if the values are near to 1, so we can put them as strong. And if the values are near to 0, we can say that our model is weak. But it is always better to express this R square in terms of the percentage of the explained variation. So hopefully it is clear to all of you. Yes. Yes, this is also known as coefficient of determination. Right. Now this R square has some issues. This R square is affected by two terms. One is size of sample. That is n. Right? Means if the size of the sample is low, then R square got inflated. We are getting a high R square, even if the relationship is not that high. And this R square is also get affected by number of features or number of independent variables. If number of independent variables will be high, then R square will be high. So this is also known as overfitting when we discuss the concept of the analytics, right? So it depends upon these two factors. So since it depends upon these two factors, so this R square is normalized or adjusted with respect to n and k. With respect to n and k. Just a moment. Okay. And here we are getting another term that is known as adjusted R square, right? So obviously for the interpretation purpose, this adjusted R square is more important as compared to R square. So what we do, we observe both R square and adjusted R square. If the values are pretty near to each other, so it doesn't matter whether we interpret R square or adjusted R square. If the values are far, it means some type of overfitting or some type of other problem is there. So in that case, we make interpretation of adjusted R square. I'm showing you these results just to give you some idea. As I have mentioned here, that like here, this R square is 0.73, adjusted R square is 0.72. So these two values are pretty close to each other. So it doesn't matter whether you interpret R square or you interpret adjusted R square, right? Both gives us approximately the same type of result. So this step is related to the strength of the model. So hopefully things are clear to all of you. Now we are going to discuss the third part or the third step. So all these things are there in the notes. So as you move forward, I will be sharing the notes. All these things are there as you move forward. So this R square, adjusted R square, even the formula are also there. So yes, design of experimentation. Okay, right? So everything is there. So I'm just explaining the concept on this whiteboard, and I will be sharing everything and the proper notes or the proper concepts as you move forward. So now we are going to discuss the third step. This third step is examining significance of independent variable or significance of predictors. Like here, suppose if we put the model, just to explain the things, suppose we put the model y equals to beta 0 plus beta 1 x1. So here this beta 1 is known as regression parameter or regression coefficient. What it gives us? It gives us the rate of change in y with respect to x, right? So if beta is 0, so obviously the rate of change will be 0. So we can say this y is, this x1 is not associated with y, right? So how we perform the significance testing? We simply examine whether this beta is 0 or not. So if the beta is 0, then obviously insignificant relationship. So what we examine, we examine H naught as whether a beta is 0 or not. So if beta is 0 means that independent variable or that predictor is insignificant. It is not contributing to the model. How it is being done? We test it through t-test. And accordingly, we go with the p-value. And if p-value or significance is less than 0.05, we reject H naught. Reject H naught means our that predictor is insignificant. Sorry, if we reject H naught, so reject H naught means we are rejecting insignificance. So we can say that independent variable is significant in nature. So what we are going to do, we will be considering that particular table and we will be checking whether this p-value for the different predictors are less than the defined value, right? So remember, this is at 5% level. Obviously, you want to go for some strict analysis. So we can go for the 1%. If we want to be a bit lenient with that, so we can go for the 10% or the 20%, right? So I'm just explaining the things on the basis of the default value that is normally being taken as 5%. So I'm changing my screen and I'm showing you the part. So now this is the table. Now we have these predictors and this is the p-value. I have mentioned about the beta. So this is the beta. This is the t statistics, which is the test is being applied. And then we are going for the p-value. Now let us see what are the significant predictors. The first term is constant. It is the significant one, but it is not the predictor. So we are not at present taking as. So this first one, this is 0.001, that is less than 0.05. So this count per box is significant. After that, we have price charge. The p-value or significance is zero point 0.4, which is greater than 0.05. So it is not significant. The next one is this again, less than 0.001, so it is significant. So the unisex versus separate sex is also significant. Then we have this value 0.031, which is less than 0.05. So this absorbency is significant, right? And all other are insignificant in nature. So here out of 9, only 3 features like count per box, where the p-value is less than 0.05, right? The next one is unisex versus separate sex. This is significant. And the third one is absorbency. It is also giving us the value less than 0.05. So this is again significant. So these are the three significant predictors, right? Now, this, once we are speaking about this result, should give a warning bell to all the analysts, all the researchers, right? Now, this analysis is being done by a very powerful software, that is SPSS. All the explanation is okay, but what you are expecting? Earlier, as per the ANOVA discussion, we have observed that our model is pretty significant. The strength of the model or the R square is very high, but only 3 out of 9 predictors appears to be significant, right? So how it is possible that overall model is significant, everything is good, everything is okay, but we are getting only 3 significant predictors. So this should gives us a warning bell, right? So for any researcher, this should be a warning bell that why only these 3 significant predictors are there, right? So remember, this is an important step. Anyway, so now I am changing the screen and I'm going for the next part of the discussion. Then I will be coming back to this again. So we have discussed about this step. Now we come to the fourth part of the discussion, fourth step of the discussion. It is the hierarchy of significant independent variables or significant predictors. Obviously, we will be considering only the significant one because they are actually the contributing. So as per the discussion, we got 3 significant predictors. One is the count per box. We are putting them not in a specific order. We are putting them as we have opted. The second one is and the third one is absorbency. So these are the three significant predictors, significant independent variable, or yes, Dr. Larry, a number of things like price is not there, leakage is not there, comfort is not there. So there must be some error. So it should give us a warning bell that something has been missed. Now, when we discuss about the hierarchy, so then again we observe a number of things. So now we have two type of regression coefficient. One is the B. Let me discuss this concept. So we have two type of regression coefficient. The first one is B. B is known as unstandardized regression coefficient. B is the, just a moment, let me use another ink. So we are considering B. B is unstandardized regression coefficient or regression parameters. Now these B are in original unit of measurement. Right? Let us take an example. Suppose we have three predictors that appears to be significant. One is x1, other is x2, other is x3. This x1 is on a scale of 0 to 5. This x2 is on a scale of 0 to 10. And this x3 is on a scale of 0 to 100. Right? They are on the different scale. And everywhere we get the same V. Right? Suppose we get 5, 5, 5. So these three fives looks to be the same. So we can say that x1, x2, x3 are approximately same in the nature. But if you observe as per the scale, this 5 is at the top of the scale, so this 5 is high. The second 5 is in the middle, so this is moderate. And the third 5 is towards the lower side, so it is a low value. So we don't incorporate the scale when we discuss the unstandardized regression coefficient like in the output. I will be showing that. In the same way, we don't consider the unit, don't consider the scale, we don't consider how much variability is there, right? So whenever we have to develop the hierarchy should be based upon beta value. On the basis of standardized coefficient, that is beta, right? So it is always better to consider the beta value. Now here, if we actually consider the absolute value of beta. Why? Because the sign, if beta is positive, it gives us the direct relationship. Direct relationship means the change is in the same direction. If this beta is negative, it gives us the inverse relationship. Inverse relationship means the change is in the opposite direction. If x increases, y decreases, or if x decreases, y increases, right? So now we are putting the beta value, means whenever we consider the hierarchy, the beta should be considered and we will be discussing the absolute value only. Sign only gives us the direction. So what are the beta values of these significant predictors? For the count per box, this is 0.269 because it has been standardized. The unisex versus separate sex is 0.362 and the absorbency is 0.204. I'm showing you these values on this. Now you see that the three values that we are discussing here, sorry. Okay. So the three values that we are discussing here are these three. So the significant predictors are count per box. The other one is the unisex versus separate sex. The other one is absorbency. And what are the beta coefficient? This is the beta coefficient that I have written. For the unisex, this is this, and this is absorbency. So these are the standardized coefficient that are under our discussion. And the other one is the unstandardized discussion that is not being used for the creating the hierarchy, right? So these are the values that I have taken up. So it is just to demonstrate the things. I'm going back to our slides for the discussion. Right. So now as we observe this value, so here the highest value is this one, means count per, sorry, unisex versus separate sex, which is a fashion statement, which is more towards the construction part is the number one. At the number two, we have this count per box. At the number three, we have this observancy. This is first, second, and third. So this is the, since the product is quite well known, so I have taken this case just for the purpose that we know about the diaper. Whenever we say the diaper is a utility product, what things are important? So for a common man also, among these three features that appears to be the significant, I suppose absorbency should be at the top because this is the basic utility function of the diaper for the kids, right? But here, instead of absorbency, which comes at the lower pedestal of the ladder of the significant predictor, unisex versus separate sex, which is actually the design part or the fashion part, appears to be the first one. So again, it should give us a warning bell that there is something wrong, something has been missed, right? So that's why I have taken this case, and without discussing the assumption part, here I have demonstrated why this assumption checking is so important. So is it okay or any question? Yes, yes, Dr. Larry.
Yeah, you mentioned so many interesting things, Dr. Masood. And
Thank
as you
you.
were talking, I thought about what sometimes we call type 1 and type 2 errors,
Yes, yes.
which you seem to be explaining in some ways. There are situations where we should reject the null hypothesis, but we do not,
Yes, yes.
or other situations where we should not reject the null
Yes,
hypothesis.
obviously.
And you mentioned something that caught my attention. You talked about something early on referring to the epsilon, the unknown outside the model. And I thought about the sample population. So we have 300 mothers. One of the things you said is we can never know why, because we can never sample all mothers.
Yes,
But
yes.
in this case, the data is telling us based on the 300 mothers. And
Yes.
I really, really enjoy your description. I
Thank
was
you.
not aware of the term supervised learning. So,
Okay.
I thought about more what we call the design of experimentation, where you take each of the whys separately. And you shared so much. So I just wanted to say that there were a number of things I thought of, and I really have been impressed with your presentation. So I don't want to upset your flow. I'll let you get back to your description. I just thought I would mention
Okay,
the
thank
type
you.
1 and type 2 error,
Yes, yes.
the
This is
beta, because sometimes that is very important as a
a very
researcher.
important one. Yes. Okay. So just I am not taking much time. I am briefly explaining the assumptions that are required. Obviously, the discussion of the assumptions also take a longish part also. But here, so I'm showing you the assumptions that we haven't considered so far. Right. So this is a slide which is related to the assumptions. Right. These are the assumptions. Why we are discussing? Because here the optimization method that we have used. What do we mean by optimization? Right? Means here we estimated the model. So we have estimated the model means there should be some criteria on the basis of this model is being explained. And what is the optimization method is being used? We have mentioned the term error. So this error is actually the difference of the actual value, that is yi, that is also known as observed value, and the estimated value or the predicted value is y cap. What we want that this difference should be as low as possible. So what we do, we consider all these differences. But now these differences will be somewhere yi will be higher, so we will be getting positive values, and somewhere yi would be lower, we are getting negative value. And simultaneously, in order to impose the penalty on the highly deviant term, what we do, we square this. And that is known as sum of square due to error, or sum of square due to epsilon, or sum of square due to extraneous term. And what we do, we minimize this sum of square. So we minimize. So we minimize this sum of square. And this minimization, for this minimization, we use the method that is known as least square method. Another popular name is ordinary least square. And the model that is being used is known as CLRM, which is actually the classical linear regression model. So I have explained this concept through classical linear regression model, though there are other type of model also. Like in machine learning, we use gradient descent, we use stochastic gradient descent. So there are different type of model optimization techniques there. Like one optimization technique is mean sum of square. Anyway, we are not going in that much technical part. And it gives us the blue estimator. Blue estimator means best linear unbiased estimator, right? So for this purpose, we require certain assumptions. Now let us briefly test these assumptions. The first one is the linearity of the phenomena discussed. Means all beta should having single degree. So this linearity is with respect to regression parameter. It can be examined by scatter plot. Right. The next one is the independent variable is known, is deterministic, is constant, it is there. The next assumption is there should not be high correlation between the independent variable. Otherwise, we will be getting a problem that is known as multicollinearity. So here in our case, I will be showing you why we are getting this error that is known as this assumption has not been fulfilled. The features that we have taken, I will be showing you, are showing high correlation. So we are having high multicollinearity here. And because of the high multicollinearity, we are getting the problem. Anyway, we should discuss the other assumptions also. The next assumption is related to the residual or the error term. So this residual or error term should follow normal distribution. So that's why we have created the diagram, we have created the graph to check the normality. Next, the expected value or the average value of error term is 0, so it is happening error. This residual terms should be uncorrelated, otherwise there is a problem that is known as autocorrelation. And the variance of this error term should be constant, should be homoscedastic. Otherwise, there will be an error that is known as heteroscedasticity. So interestingly, the name that popular name is related to violation of the assumption. Like the requirement is there should not be correlation, but the name is normal. The popular name is there should not be multicollinearity. Right? The violation, multicollinearity is a violation. Next one is residual terms or the error term should be uncorrelated. But if they are correlated, then we are having a problem that is known as autocorrelation. The third one is variance of the residual should be constant. And if that is not constant, so that is the problem is heteroscedasticity. These are the assumptions that are required. Since we don't have the much of the time, So I'm just mentioning about the first one, that is known as multicolority. And here we are having this problem that is known as multicolority. So multicolority, we always say that it is a rule, not exception, right? So why multicolority is there? Because the features will be correlated and we know it very well. Like I am showing you the features description. Now, let us look at the features. If some mother thinks that count per box is important, so for that mother, price will also be important. So they appears to be correlated, right? If for someone price is not important, so expectedly count per box is not an important criteria to decide it. For some mother, absorbency tendency of the diaper is important. So for that mother, leakage should not be there, comfort should be there. So they appears to be correlated, right? In the same way, unisex versus separate sex is a design or the fashion statement. Style is also a fashion statement. So they are pretty close. They are showing pretty high correlation coefficient. So we know very well before start of the discussion that we will be getting this problem that is known as multicolority. So why we, since we know from the word go, so why we have taken these features? The reason is we take a number of features to measure a thing just to reduce the measurement error. Measurement error means the difference between what we want to measure and what we are getting as a measure, right? So as we increase the number of rater, if we increase the number of measurement things, number of features, so obviously the measurement error decreases. So instead, like we know that count and price will be related, they will be producing multicolority. So why we have taken both? We should have taken only one, that's the price. So why we have taken both? If we take the price, then multicolority may not be there. Multicolority may be reduced, but on the other side, there will be high measurement error, right? So that's why we always say, specifically in the cross-sectional data, that multicolority is a rule, not exception. It will always be there, right? And let me show you um, just a brief idea about the correlation coefficient. So here I am using this. Yes. So now if, just a moment. So this is the correlation table, right? Just to give you the basic idea that we are expecting multicolority in the very start, right? Now this is a symmetric matrix. Symmetric matrix means we are getting the similar term on the rows and similar terms are the column, right? And like here, this 0.669 is the correlation coefficient between the brand preference and the count per box. In the same way, 0.669 is the correlation coefficient between count per box and the brand preference, right? So we are having two equivalent triangles. So we are considering only one triangular, that is known as upper triangular. So we are considering only the upper triangular. So I am taking this upper triangular. Right. Now here all the diagonal terms are 1. So we are ignoring this diagonal term because they are showing correlation coefficient of, like here, unisex versus unisex with unisex versus unisex. So if we calculate correlation coefficient of x with x, x1 with x1, we will always be getting 1. So they have no importance. In the same way, the first row is showing the correlation coefficient between the dependent variable brand preference and other features. So that is also not required for the discussion of multicolority. So we are ignoring this. Now let us consider the other features like here. This 0.864 is a high value, and it is a correlation coefficient between price charge and count per box. This 0.69, that is zero point 0.7, is the high correlation between count per box and the value, right? So we are getting a number of high values. This 0.849, sorry, 0.894, this is the correlation coefficient between unisex and the style. So they are showing high correlation. This 0.942, this is a high value, very close to 1. It is showing correlation coefficient between absorbency and the leakage. So we are getting a number of terms that are showing high correlation. So from this elementary table or from this this basic table that is part of exploratory data analysis, we are having the idea that multicolority appears to be a big problem here. And because of the multicolority, we are getting this type of absurd result. Though here the proper measure of the multicolority is the VIF, that is known as variance inflation factor. Yes, this is VIF. So if we are getting high VIF, means normally the VIFs are more than 5 or more than 9 or 10. So we are expecting high multicolority. So here the two values are near about 10. So here the problem is of the severe multicolority, right? And because of this severe multicolority, we are getting this problem. So I'm just putting you on this screen. Yes. So like these are the discussion related to multicolority. Now I suppose I should stop here. So yes, obviously number of slides are there related to the different assumptions, but that will be taking much longish time. So this is from my part. So I will be sharing these slides if you people require. So now, so this is from my side. Yes, please.
Yes, Dr. Masood, I was looking at your data. I think you referred to that VIF. Does that relate to the beta? I noticed when I looked at the data, the column beta was very low and the VIF was very high.
Yes.
And so does that mean that we need to revisit that because of a
Yes.
false positive?
Yes, definitely. So we have to, this VIF indicate that there is a problem of overfitting there. We are expecting high multicolority. So we need to do something so to control that. So there are a number of things like we can go for the principal component analysis. We can go for the regularization like ridge regression, lasso regression. But what is important for a researcher, researcher should identify then in spite of using software, if the assumptions are not being fulfilled, so we are committing some error. So there are a number of remedial measures, number of remedies are there. So to reduce the ill effect of violation of the assumption. But what is the important thing? That we should observe, we should sensitize the researchers that there are certain errors that needs to be means there are certain errors in the term of violation of the assumption, so that needs to be taken care of. Once we notice that there is some violation, there is some error, then we can eventually be finding out how this error or these things can be controlled. But if we don't notice, if we don't think that there is some error, then obviously there will be a darkness and we don't know that there is something good that we can need